We are live from downtown Mill Bay. We really are live from downtown Mill Bay. Now they were running around trying to get these to work. And I wonder if I can turn it. And he came in here several times going, no matter what we do, we can't seem to get suction. And I said, would this help? And I turned that. In every suction machine in any lab I've ever been with, there's always a baffle that shuts it off. So they're all shut off. I think they're running around trying to get them to work.
So will they work?
I think so. You do have to turn them on. Let's see. So the green light is on. That means the motor. Now, they were getting the motors going, but I don't know if they have those, like, when they're not testing them. Is that on? It was very quiet. And there's no set. Oh, hold it.
Could you try turning the?
No, that's on. Any system you ever use, whether water or gas, because it's universal, inline is on. So that means it can flow. Crossways, because it's visually obvious, means it's off. So yeah, if you ever see that system anywhere, that's there. Oh.
Good morning.
Good morning.
Do you know where the other scales are?
No, I have not yet found them. When I saw Lily get scales, she went into the lab and she went right. So I look in those drawers. There doesn't seem to be any other knobs that. I actually feel a faint breeze now. And all it needs is a little bit, so it might actually be working. We'll have to try it. Yeah. If I turn it on, I do believe it's not really possible to shut it off. Oh no, now that's working. Oh, they're getting better and better. Okay, that all aside, we got all the way to here, did we not? We finished that. Maybe. How much time we got? 18. We got some time for that. No, I think it's time for some solidification instead. Given where we are. One second. Oh, it's awfully formatted. Take that one. We will do that. Formatting looks like it got messed up. Okay, we're going to do Bohr model. But first I'm going to teach you how to count electrons. We did count electrons last day. So let's just quickly make sure we're on the same page. Block, Guns, Alexander,
Here.
Aria, Ariel,
Yeah.
Charlie, Peng Chao,
Yeah.
Eric,
Yeah.
Guy, Isaac,
Yeah.
Isabel, Jessica, Katie,
Yeah.
Kiana,
Yeah.
Natsuho, Sihu, Sterling, Jaden, Tom Bowman. No Tom, Tyler.
Yeah.
Excellent. So, here at table out, what is the number of valence electrons in fluorine?
7.
Joe, you just called it out. but I ask it and then I'm gonna pick a name. What is the number of valence electrons in sulfur? JD.
6.
It's like it new. What is the number of valence electrons in gallium? Isabel.
Oh, 3.
3. If you ever can't find an element, because of course I'm looking at it, I find it quickly, you can get its atomic number. You have an alphabetical order version. So just put so you can, if you know the name, you can quickly get the atomic number and then find it in the periodic table. So does anybody not know why element 31, gallium, has 3 valence electrons and not that huge number in between? We did that at the end of last day. Okay. Good. Excellent. So, in your notes, draw the Bohr model for sulfur. And do it, this is one circle and dot, where a circle and dot is actually helpful. And then we will do the Lewis. Eric, how many protons does sulfur have?
16.
16 protons. And for this purpose, we're not going to worry about the number of neutrons. And how many in the first shell? Kiona? 2. So 1 and a. Oh, Kiona, how would you place them? Where'd the second one go? Where's Kiona?
Well, I put them together.
Excellent, well done. Next shell, Tyler?
8.
8. How would you place them?
Together, like top, left, right, and bottom.
One of the things I do out of habit, and this is going to be useful for Lewis dot diagrams, I put them 4 on singly, and then I start pairing. It doesn't matter which direction as long as you're consistent. And then how many in the third shell? I may have drawn this too big, and I'm running out of room. Oh yeah. 6. And how are they placed?
2 at the top, 2 at the bottom, 1 at the bottom.
Ooh, excellent. Anybody do that? Did you put up your hand? Yeah. Yep. This is one of the exclusion rules from quantum that we put into the board. If there is an empty space, an electron always has to fit it if there's one available. So that's why when I say I go around, I go 1, 1, 1, 1, pair, pair, and then pairing again as you need to. That way you'll always have them spaced out. It's like, again, the bathroom stall method. I mentioned the bathroom stall method in this class. Oh, you walk into a bathroom and, I don't know, movie theater, big bank of bathrooms, nobody's in there. Which stall do you take? Obviously the last one, because you want to be away from everybody else. So you go into the last stall. Someone else comes in. Which stall did they take?
The one, like
Closest to you?
No,
Middle
closest
somewhere.
to you.
Yeah,
Closest
they're
to the
yeah, they're gonna take one away. So there's all these bathroom stalls. The bathrooms, the bathroom stall theory of electron shell repulsion. boom, 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 is that, let's say you take that one. Are they going to take that one? No. Maybe they take this one. I'm deliberately doing something. Someone else comes in. Are they going to take that one or that one? No, everybody wants to be. But only once they're all filled up, then do they start pairing. Electrons work exactly the same way. And that's because electrons are also, what charge are electrons? Negative. And what do like charges do?
Repel.
They repel. They don't like each other. Now they do pair up. The reason they do pair up when they're forced to, they actually change a property called spin. So if you go on, you'll start actually representing electrons like this, where you give them a little tail and they have opposite spins. But they're both negative. They don't really like each other. It's more that they really love the protons. The protons are positive. They want to get as close as possible. But if they can spread out, they would spread out. Now, if we're to do a Lewis dot diagram, number one, if we know it's sulfur, then the number of protons is superfluous. Sulfur always has 16 protons. So we just write in the element symbol. And then, how many valence electrons? 6. And you do it exactly the same way. 1, 2, 3, 4, 5, 6. And that's Lewis diagram. For individual atoms, anyway. Do all those. And find a spot on the board and do them. Jaden, you can join any group you like, or you may lone wolf it. I leave the choice up to you. There's the boards at the back as well as front, because it can get a bit crowded, and we're not going to get our nice big whiteboards anytime soon. Grab your partner, find a spot. Someone spelled con in whiteboard pens at the front. That way I can quickly see how everybody's doing.
Which one are we doing first?
You're doing all of them. Just do all of them.
Also, they give us different ones for like this one. This one. Yeah, let's go with it.
Is it really? Hold it. N O C N O C N A K. K is not on there. C L.
That one inside.
Yep. Do all of them. All the ones you can find. Apparently the big list and the little list is different. I don't know how that happened. Do all the different ones. You don't have to do one twice because that would be silly.
Which one do you want to do? Which one?
What?
Let's do carbon.
No, we have to. Let me do all first.
Wait, we need to do one of them or all of them?
All the different ones. Apparently these two lists are different. Oh, I know why they're different. Sometimes I just ask you for the number of valence electrons in case you start, but just do all of them.
Oh, so like.
So if they're duplicated, don't do it. Do it only once, but all the different ones.
Oh. Wait, N O C.
Okay, and then back up and do something.
Yeah. What?
Okay, we can any issues about that?
Let's make it smaller.
Yeah.
Bannon.
Okay. So, SE is 6.
So let's go with
MA is 1. I is 7. F is 7 also.
I did all of them, but I just didn't repeat ones.
yeah. You don't need to repeat them. That would be silly.
K is
7.
1. A 2 and P. That's fine.
We already have an A. Oh, do we have F? No. F. C A. Do we have phosphorus? No. Oxygen, iodine, selenium. And we have carbon. That should be. I get 11.
Yeah, it's 11.
Everybody, look at the board. Do you see your group number? Write down your number. 5, 4, 3, 2, 1, 0. Elect a member of your group to come up and put the correct dots around the right one. While I check these.
Yeah.
Nice.
Amazing.
Nice.
Did that say G?
Ooh, nice placements, whoever did that. Ooh, organized.
Wait.
Hey, I'm number 1, girl.
Oh, we have to do it on our numbers? I don't know what number I was.
New.
Bro, you did it wrong.
Nine.
What do you mean I did it wrong?
Yeah, it's like 1.
CA.
Bro,
Counts
you
one,
did
yeah.
mine.
Here.
Good.
Wait, pause.
It's okay, it's okay. I don't care.
Well, I don't know which one I am. Oh, yes, I'm awesome. Here, erase it. I'll erase it for you.
Oh, Andrew, thank you.
There you go. Where's the marker? Is this marker? Oh, I'm so smart. This is so cool. I don't know which one I was.
Oh, good.
I have to go check.
You don't know what number you are? No. I'll put it back up.
I think you're number 10. That's like the only one that isn't number 10.
There. No, there is no 10. There's only 1 through 9.
My bad.
And who did twice?
Hmm?
Okay.
No one did this.
Is 11 done? 11
10
done.
and 11 all into
Excellent. Well, that was quick. Okay. There's a bunch of stupid rules. Now I'm going to show you how to use them. And I say that because if you read through the rules, to me, when I learned it in university, it didn't make sense. And I'm going to do it this way first, and I show you. I think it's a lot easier. First, you write the compound down in a way that you can get the number of valence electrons. So you go H, and there's 2 of them, oxygen, and then if there was any charge, you'd put it here, but there isn't, so we just go there, and I might put a little X there just so we know it's oxygen, not 0. That's a 0. So how many valence electrons are in hydrogen? 1. And we have 2 of them, so there would be 2. So there's 2 electrons. How many valence electrons are there? Stop it, Arm. How many valence electrons are there in oxygen?
6.
6. There's only 1 of them. Now, if it was a negative charge, would we add or subtract electrons? Add. And if it was a positive charge, we subtract. But since there's nothing from the charge, it has no charge, we put 0. And then we have 8 electrons. We are also attempting to obey. We go back here, and this is the key point. This is the part. The octet rule. Everything needs 8 except for hydrogen, which likes 2. So we put in the middle the central atom. How do you know which one's the central atom?
Oxygen, because there's only one.
There's only 1 of them. It's usually the one in the fewest amount. So you put it in the middle. You put everything else around it in like compass directions. You are also making a 3D product on a 2D board. So no matter what you do, it's going to be a little off. So we will now put hydrogen in. I'll make it a different color. Since hydrogen is water, I'll make it blue. And so now we have our central atom. We have our outer atoms. And you encircle it. We don't attach them to each other. They encircle the central atom. There are times in which they'd encircle it, but that would have to be given to you in the question, would show it to you and so forth. We go back to our valence electrons, and the first thing we do, bond to central. So, boom, boom. And we account for those electrons. How many electrons are in a bond? 2. There are 2 electrons per bond. And so we go minus 4 electrons. Only 4 electrons left. 2. Put electrons on outer atoms to fill octets. How many electrons does hydrogen want?
2.
2. Is it happy? Yeah. It's got 2. It's got 2 in the bond. It thinks it's happy. Even though they're sharing it, this is covalent bonding, it thinks it has 2, so it's happy. So we don't have to do anything for that. You wouldn't write minus 0, but because I did that in a different color and I'm doing it here, I'm just being really pedantic and showing that. If you just write down what you minus every time. Then, last step in this particular case, 3. Put rest of electrons on central atom. And so now, what 2 spots are left?
Like the top and bottom.
Top and bottom. So there's only 2 spots. We can't just put them anywhere. So we have 4 left. 1, 2, 3, 4. We're done. Now, last step. 4. Check. Octet rule. 5. Increase bonds. I should probably write that out rather than shortcutting it. Increase bonds if needed. If satisfied, stop. How many electrons does oxygen think it has?
8.
8. It's got 4 shared, These are known as lone pairs. Lone pairs, and that's a bonding pair. Now you've probably seen water doesn't usually have straight lines like that, and part of this is because we're doing a two-dimensional model on the board for a real three-dimensional thing. I don't know where they've hid the balloons. Have I marked a model set? Someone has stolen my Norco model set. Someone has my snippets. These aren't nearly big enough. Those will work. In terms of what you're looking at, anything that has an octet has 4 spots for those electrons, and since everything wants 8 electrons that we're going to do in its outermost shell, so you got 2 that are bonding, but you also have those lone pairs. And I'm going to represent those lone pairs with this really long skinny ones. So they're not bonded to anything. Those electrons are just here. And electrons are what charge again? Negative. So they push down the other 2. So it's not really the 4 corners of the compass. If we drew it properly, 2 of them going back, because they're all perfectly equally spaced. Because if they're trying to get away from each other in 3 dimensions and not 2, they're going to rotate until they're this tetrahedron structure, not a 4 cross. The 4 cross is just the easiest way to represent it on a board. So that's what water actually looks like. And that's why when you see representations on it, like television stuff, you get Mickey Mouse ears. Because they don't show the lone pair electrons, because they're not holding anything, so they're invisible. But the reason that it's that way is those lone pairs in their negative charge is pushing against those electrons in their negative charge. And they want to get away from each other, and that's why you get that structure of water. So now that we have a Lewis dot diagram, we've bonded it correctly, that gives us a hint into its structure. Later grades, you get more into 3D structure. We're not going to worry about the 3D structure. We're going to stick to the 2D and make sure that we can get to the correct 2D structure and the bonding pattern, but that's how you do it. Now I am going to now, this is probably going to be highly irritating, but if you have room anywhere, or a separate piece of paper, I'm going to do it again. But I'm going to do it the traditional grade 9/10 method that you would do. That will actually serve you in a lot of these cases. It is a little bit easier. In some cases, however, this just doesn't work, or you just have to get a little creative with it. You're allowed to use either one. Having both in your pocket is useful. So in this method, you just draw them as you did. So we have hydrogen, we have another hydrogen, and we have oxygen. Valence electrons on each hydrogen. 1. So let's 1, 1, and I'm going to group them. Valence electrons on oxygen. 6. 1, 2, 3, 4, 5, 6. So we've gone from atoms. Now we're doing compounds, and we're specifically doing covalent compounds. And then you just sort of look at it and go, every electron will eventually want to be paired, and oxygen wants an octet. How could we move these around to give it an octet? Yeah?
One hydrogen electron.
Yeah. Now, so on your piece of paper, drag the hydrogen you just got down to there. And unless you have an iPad, none of you can do that. So what you do with this, you usually draw it somewhere close by, and then you just go, oh, these can bond. And, wah, my elbow is making drawings. And they go, oh, those two can bond. Then you just redraw it. You go, okay, those bonded. So I've got oxygen, boom, 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 boom. Hydrogen, boom, boom. Hydrogen, boom, boom. And you just have to remember, hydrogen to oxygen to oxygen. Is that the same drawing as before? Same thing? Anybody think it looks different? Same thing. We've just drawn it this way, whereas before we drew it that way, straight on, and you saw what I'm talking about. So we got two lone pairs, we got two bonding, and we just went, oh, we match them up, draw it like that, and go through. You don't have to do all those rules about counting electrons. You put the valence electrons right on there. The counting rules work really well in Chem 11. That's the method we teach you in Chem 11. Because then you have to put double bonds in sometimes. Well, you're going to get double bonds here in grade 10 as well. And it can just be, it can be simpler for some of them and more complicated for others. For something like this, it's probably more complicated because you can just do that. This method, you are pretending those electrons belong to one of them, and then you join them up. In this method, you take all the valence electrons away from them, none of them belong to any of them, and you dole them out until you get the correct structure. That often works really well, because although we may think those electrons used to belong to one or the other, when they're shared, they kind of belong to neither, and we can just sort of spread them around, make some structures easier, either or. So, using any method you see fit. Make methane. Oh, you should know the name of this. This is methane. Methane gas. You can burn it. There's a whole subsection of naming that you can do here. C2H6 is ethane. C3H8, ethane is propane, that's propane gas. C4H10 is butane, like in your lighters. Anybody seen a pattern to the formulas? Yes?
C and H.
There's C and H. Mathematical formula? Every time C goes up by 1, this is going up by 2. If I went CX, H, is it 2X?
Yeah. Oh,
No.
X plus 2.
Yeah,
oh, it's 2x plus 2.
2X plus 2. That is for all the straight chain carbons. And the naming goes methane, ethane, propane, butane, and then after that gets easy. Pentane, hexane, octane, nonane, and decade. You start using all the Latin roots, and that's how you name all the organic molecules. So when you see like hexyl chloral ethane, ethane is 2 carbons, hexyl means 6 carbons. They're using them in a particular way, but you can now start to figure out what it is. Anyway, the only one you have to know is methane. Write down the structure. I will ask someone to give it to me in a second. Did you say it? No. Oh, nope.
Could you go back to the exercise?
Oh, yeah. Sorry, did I move on too quickly? I moved on too quickly. There you go. Finish those. Actually, if someone said I don't know, maybe that I'm doing this. I love Lewis dot diagrams, so I may be expecting you to get it a little too quickly. Maybe different group stuff. Let's do methane on the board, and I'll just duplicate it up here. Find your new people. Isabel, you can join any group or lone wolf it. Up to you. Dealer's choice.
Oh, let's go.
Go. Find your people. Does everybody know what group, who they're with? Anybody not know? Okay, put her down.
What do we do? Methane.
Methane.
We're all doing
All do methane.
Alex. Stay there, Alex. Stay there. Wipe this off.
Da, da, da.
Is this correct?
Yep.
Ha.
Nope. Who's your partner? Oh, who, did you not find your partner? Go consult. Not that. Do it on a board somewhere so I can see it.
It's just on finding angles, right? Yeah.
On the board somewhere? Oh, you've got a board right there. Are you not working somewhere? But fire it up. Oh. I switched it, but then I thought I said, hey, anybody not know who their partner is? But go find your partner. Jaden, where are you? There you go. Go find Jaden.
Oh, okay, so no, that's somewhere easy. Yeah, it's pretty easy.
Pardon me?
It's pretty easy.
Hmm. Nope. Yep. The reason this isn't good is that you've done circles. It just makes it confusing. It starts looking like you're doing electrons and not Lewis dot diagrams. So if you erase the circle and you left the lines, you'd be good. 2 for 8. Very quickly, we've got carbon. It's the central atom. It has 4 valence electrons. We have 4 hydrogens. It has 4 valence electrons, 1 each. We have a charge of 0, and so that's 0 changes. So a total of 8 electrons. Central atom is carbon. We have arranged the atoms around the central atom. 1, 2, 3, 4, as it looks like everybody did. Then you count. Hydrogen's happy. 2, 4, 6, 8. Carbon's meeting the octet rule. Done. If you did it the other way, and in this case, I don't think either method is all particularly faster. One might be easier to understand. You go 1, 2, 3, 4. Then we've got our hydrogens. 1, 2, 3, 4. 1, 2, 3, 4. And then you have to these bond, which if you drew them nearer to each other, Mr. Neufeld, this wouldn't look nearly as confusing. But we get them all together. And then we know each one of those is a bond. So then we get carbon, bond, 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 hydrogen, 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 because each electron is in a bond is treated as a line. So 2 methods, exactly the same result. meets the octet rule, we can stop. We're going to find ones that don't meet the octet rule, and we're going to have to do an extra step once in a while. So the last thing you should always be in the habit of doing is, even after you think you got the structure, is it the right number of electrons? So one of the reasons you're putting the valence in there is, 4 and 4, there, you can only have 8 electrons. So more than one person showed me this. And that's 2, 4, 6, 8, 9, 10, 11, 12 electrons. You have too many electrons. Also, that carbon is not meeting the octet rule because that carbon seems to have not lone pairs, but extra electrons attached. It's going to be very unhappy. So too many electrons. You want to make sure that you don't exceed it or go under, and you have exactly the right amount. And then after you make sure they have the right number of electrons, are they happy? Are they meeting the octet rule? Next one. Did that one. NaCl. That's a little different.
Same pair.
This one I'm going to say, we don't do ionic as much, but I'm going to say right now, just in your seats, give me the Lewis dot diagram of each one individually. The rules I was showing you before work really well for covalent. What type of compound is this?
Ionic.
It's ionic. And we haven't reviewed ionic yet, but how do you tell that it's ionic?
Because between that's just two.
Pardon?
Opposite.
Sorry,
Same thing.
Mr. Hackerton, you're so loud behind me. I can't hear anything basically. Say it again.
Just because I don't know why.
You just know it is. You feel it in your gut. Yes.
Ionic is between one nonmetal and one
Right. So if you see a metal and a non-metal, it's a pretty good indication it's ionic. Bonus points. Does anybody know an ionic compound that is only made of non-metals? Grade 9, did you see this? As a compound?
Maybe.
Maybe. That's ammonium chloride. Later on, we'll do what's called polyatomic ions. So it is a covalently bonded, we'll do the Lewis dot diagram of that, compound that has a positive charge that can then ionically bond with chloride. So it's not metal and a non-metal, it's positive and negatively charged, which is 99% of the time metal and non-metal. But there's a few ringers in there. Okay, Lewis dot diagram for these. Sterling, sodium.
Sodium. I wasn't able to find it online.
It's on the left of your periodic table, couple down.
Oh, okay, so one.
One of them. Boom. Valence electrons in chlorine. Jessica. Question?
Oh, I know
Oh no, I'm asking Jessica now. Which Jessica?
that.
There we go. 7. How would you arrange them?
2 at the top, 2 on the right, 2 at the bottom, 2 on the left.
Right. Now, unlike covalent compounds, we don't join those up into a bond. Because in ionic compounds, what has happened with those electrons? Yep. You transfer the electron. So you go, oh, this electron's actually over there. In fact, just to illustrate that point, probably good if I made that a different color properties. Let's make it pink. And then to show the ionic compound, we put square brackets around it, and we go, oh, what charge is chlorine now?
Negative. 1 minus.
-1. And sodium with nothing in its valence shell is
Plus 1.
+1.
If we don't have different colors, can we just use like an axe?
Oh, yeah, you can do whatever you'd like. Yeah, no, that's fine. I just changed it to pink to stand out against the green.
Is that pink?
Yeah. Yeah. Do you not think it, what color do you think it is? Hmm? What color does it look like to you?
Red.
It does look like something called red, but red doesn't exist. Red is just dark pink.
I'm sorry.
Yeah, because Hope House owns red.
Okay.
Yeah, just like Allard's color is technically blue, which means Privet owns Allard.
Is it different type of blue though?
Privet owns all blue. Our house color was blue before Allard even had a house color, and we took all of it.
Is this even about science anymore?
Pardon?
Is this even about science?
Yes, yes, it is. Mr. Wismer started as a BFA in what house? Privet. So we own Ellis. Mr. Collis Hanford was a graduated Old Brentonian from which house? Privet. So we definitely own Ellis. Mr. Barrett started out as a BFA in Privet House. We trained him. Ms. Ramsey. Which house is her son in? Privet. Yeah. Yeah. Interesting. Yeah. Not saying anything. Not saying anything. Not saying anything. Okay. And show me them in a moment, but just start off trying to do them. Do your best.
Come here.
Put them together. Any method you want.
You're right.
Good final structure. Remember to check the number of electrons and the octet rule for everything. Yep. Stop at number 6.
Oh.
Yeah. I mean, obviously, and if you're like, I know this, yeah, you can keep going if you want.
Choose one.
What time are we at? 9:04? Ooh.
7.
And I am going to blank the live stream for a second. Although it's still on, so.
Wait, for H.
I think it takes like one.
Oh, I'm not going to confirm any answers. Confirm with the people around you. So, check your answers against others. It has a total of a +1 charge. Yeah. That's a good question. Consult. Because you might have that question on the board. Yeah, you can go on the board and do it. That'd be brilliant.
Mr. Newfeld? Mr. Newfeld?
Yo!
When in NH4 plus 1, where does the where is the missing electron? From which atom?
Yeah, I don't know what you mean. That's like, for NH4 plus 1, where is the missing electron?
Like,
It's missing.
from which
And
atom?
so
is
it's
missing?
not anywhere. Pardon?
From which atom is it missing?
You know how the first method, you just count the electrons and you don't care where they came from? It's kind of like that. It actually doesn't really matter. It's just not there. So you have to, so the total number of electrons, no matter how you do it, just has to be one less.
Yeah, but it has a charge, so we have to represent that, right?
Now, enter.
No, but because it has a charge, it can count because if it didn't have a charge, then
Yeah, I know. Should we do the? Should we do the?
Up to number 6.
Square brackets.
if and only, to put the charge on it at the end?
Yeah.
Yeah, you can do that.
Wait, but which one? Why would you need the bracket?
Just to show the charge for any.
In each one. But it's not ionic.
I know.
Yeah, how do you show the charge?
It's just to show the charge. You said we don't have to, so never mind.
I think we need to.
Oh, you do have to show the charge.
Oh. But so that's how you show the charge?
Yep.
Okay.
What for this?
No, for +1, you just show the charge by right. +1 in square out, like outside the square bracket.
What?
I just did this. This is used to square bracket.
And how many examples do I have? So we're doing HCl, 1, 2, 3, and 3 examples.
Wait, because oxygen only has
Sure.
6
Good
valence
makers.
electrons, right? This counts as 2 electrons, and this counts as 1.
Mm.
And chlorine only has 4, so here's 4. Here's the other 2. Here. Sorry. So drop carbon first, go this. And drop
There's
oxygen.
total of
So these
4 plus 6, 10 grams.
Does it have to satisfy the octet rule?
Yes. Well, which element does not?
CO2?
Which element does not have to satisfy it? CO2, every part of it does.
Sorry. Hydrogen.
Hydrogen doesn't have to, but carbon needs the octet. Octet applies to atoms.
That's
We can
6.
just have.
No, that's not how it
Yeah.
works.
Well, we don't have enough electrons. And,
You need double bonds.
you need double bonds.
How do you what?
There's no such thing.
Do you ammonia?
2 bonds.
Oh, whenever you
Is it
charge
seven or
square
seven?
brackets, charge on the outside.
It's 7, 7, and then 2, so that there's 12 left, so 1, 2,
Is that
Oh, you got your bonds, is that
6
your
on each.
So 12.
and then the middle bond is 2, so that equals
What you're doing is you're putting dots at either end. So technically every line is 0 electrons, so when you put dots, that's 4.
the bond
So
is
you don't want to
1,
do
2, and you're sure.
But then there's an extra line, you can draw next to one of them.
So that would be
Why
the one
Has,
that
there's 9.
But if it's worth
Do we use
if
double
it's worth
bonds?
2 here, wouldn't that be worth 4? Or is it 2 like universal?
Because it's shared, so
Anyone on CO2?
So both CO2 chop with 2.
Are you using
yeah,
this
so
is-
both of them get 2 from this,
I think
but
this
it's
is
still
the-
worth 2.
I hear good discussion going on.
C should have.
No.
Yeah, but oxygen still doesn't. Yeah, I still have so. Are you sure?
Double bonds.
You use double bonds? Okay.
Unless there's.
If I'm not wrong, you have to keep on. Or probably mint.
put it back here, turn that back on, put it back there. I've divided the boards up. Groups 1 and 4. If you're fairly lucky, head on over there and show me your best HCL. Show your workings and whatever you want. Got the whole board to show both methods if needed. Group 2 and 5. You can work separately or together, group 2 and 5. I would like to see NH4 plus. And group 3 and 6.
Okay.
You are here for CO2. Oh, with your work here, you actually, this is yours? This is, you're on the right track, especially with CO2. But the part that's wrong is, how many electrons is that? That's 4, because a line wouldn't use 2. So just don't put the dots in the end. If you don't have the dots in the end, you should show the rest of your group. You've got something going on there.
Where's F?
Yes.
Where's F2? Where's F2?
F2?
Does it matter? Which one should group
Did I skip F2?
No.
I just knew.
Group 4, yeah. Which one should group 1 do? Well, like,
Group 1 and 4 should do HCL. Actually, did I skip F2?
You were right.
we can do it.
Oh, hold up. 1 and 4, 2 and 5, 3 and 6. So group 2 is there. Sorry, I thought you were saying F2, and I didn't know I gave that an example.
Okay.
Which one are you? That's good. Once your group have something and you agree, sit on down. You can help others if needed.
Oh, wait, no, we're group 3, never mind.
So we should be doing this.
The double bond. So oxygens have 8
You're basically just
Yeah. Well, you counted 4.
So we give 4 to the central one, so they can share.
all of the one.
Right?
You're enough money.
Yeah.
You're right. You're right.
What?
Once you have your final structure, head on down when you're happy with it.
Yeah, looks good, man.
Looks good. Looks good.
Carried my team.
Just out of curiosity, which one's your final structure?
Oh, the first one I drew just to
Just
remember what
okay.
it was.
No, that's okay. Working.
And then pull it up.
Draft. Like a draft. Good. 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 What's wrong with this one?
No left electron.
Not everything. The bond's good.
The electron
Eric? The valence electrons, yeah. So, for this one,
Oh, I took the marker.
at the back, gentlemen, always do a final check. This one completely disobeys the octet rule. Chlorine is incredibly unhappy. It doesn't have 8 electrons. Hydrogen happy, this one's not. And too quick, you need to account for the fact that you're doing your valence electrons. So either you're starting out like this, and you have it accounted for, or you're starting out like this, and then you're accounting for it in that way. You go, oh, I minus 2, 1, 2, 3, 4, 5, 6, minus 6, and then you get it. If you just look at it and try and do it, you'll often find yourself doing that. So be careful with that. That's good. That's good. That's good. This, good. So I know there was, I overheard a lot of discussion on that one. And so I will quickly whip through the, hold it, where did my pen go? There it is. Have a seat. Gentlemen over here. If you do this the dot method, the double bonds pop out naturally and it works really well. Because we can see carbon has 4 open slots. There's 2 slots on the oxygen. It doesn't always work this well, which is why the other method exists. But in this particular case, this is fantastic. So you can join them up and you can see where they join, like that carbon. So you clearly get oxygen has 2, 4, 6, 8. Oxygen has 2, 4, 6, 8. Carbon has 2, 4, 6, 8. Everything is satisfying the octet rule. It is wonderful. Yes?
Do you pair the electrons for the...
Yep, they're paired. And they're paired on there. Yep. Yep, they're paired. Because they're already paired here. So when you take those singles away, they're paired. So those slots are used up. They're just used up for the double bond. Now, if you were to do it the other method, and you have carbon, 2 oxygens, plus or minus 0. Carbon has 4, 12, and then 0. So we end up with 16. We make our central atom. Oxygens on either side, and then bond once. Those, each bond is 4 electrons. So we have 12 left. We put those on our outermost to begin with. 1, 2, 3, 4, 5, 6. Octet rule satisfied. 1, 2, 3, 4, 5, 6. Octet rule satisfied. That's 12 electrons. So we perfectly did it. We can't keep going. I can't put them on the central because we have none left. We used up all 12. Is carbon happy? No. So when you get to this point, you go, carbon's not happy. In the other method, you go, oh, well, I just take those. No, I wanted to draw. I just want to draw a different color. And you take those and you turn them into a bond. And you go, okay, now carbon is 2, 4, 6, still not happy. We're not going to take all from the same. We switch sides. Take from the other one, and now you're done. Little bit more to get there, and this one's probably more work than the other method. There are times with the other method it's not nearly as obvious. The time and those times are when you have a lone pair and you actually have to break it in order to make the proper bonding. That's a little bit more obvious with this method. But for CO2, it works fantastically.
I've paired the electrons.
Your, your electrons are paired, yeah. Oh, there's a couple people that did bonds like this.
No, because see, these count as pairs, right? So
If,
this bond
gentlemen,
represents a bond.
one second. If you are leaving your dots on either side, this is technically communicating 2, 4, 5, 6, 7, 8 electrons. So erase your dots, put in proper lines. Anybody here gone to a Swiss or German school before this? For your lone pairs, I forgot to mention, have you seen this before? And so you're probably used to this. And they would make it like that. Yeah? Yeah. And, well, they do that because they're trying to represent the 3D because they're not obviously H60. Anyway, lone pairs can also be lines on the outside if you want. And that both of them are accepted. It's just Germans tend to do that more often than everybody else. HCl was fairly quick, either method. That was good. The only thing is the NH4. If you're doing that, you do have to account for the missing electrons. So nitrogen has 5, 4 hydrogens has 4, and then plus 1 as a charge has minus 1 electron. So it is actually 8 electrons, not 9. Central atom, hydrogens all around it. 1, 2, 3, 4, 2, 4, 6, 8, minus 8 electrons, done. I find that for this one, that method seems a little bit easier because if you do it the other method, you have nitrogen, 1, 2, 3, 4, 5, and then you have hydrogen, 1, hydrogen, 1, hydrogen, 1, and then hydrogen, 1. And then the question came as someone asked, which electron do you remove? Yeah?
I asked.
Pardon?
I asked.
Yeah, you did ask that. Which one did you remove?
The what? Doesn't matter. One from the
I think the one from the end makes the most sense because then visually you go, oh, I join, and then you get the same structures over there. However, if you didn't, it honestly doesn't matter because let's pretend you actually got rid of, come on, you got rid of one of the hydrogens. Well, then that hydrogen has no electrons. You just pop it on the tube, and you can still join them up and then get the same structure. But you just have to be a little bit more creative about how you do that. So when there's charges around, I really like this method. When there's no charges around, oftentimes this one's really good as well. Ooh, N2. NO3 minus 1. CCl4, OF2, SO3, O3. Lovely. I'm going to work on those. Last look into the box. I am going to post a review sheet for your quiz next week. And then you can work on your quiz tonight for prep as well. It will have review questions for stuff we've already done. I will also post the answer key after a day or so that then you can check your. Yes. As soon as I mark them, I wanted to mark them today, but I just didn't. So I have a 3-block last block. They might be marked today. Yes. For which one? Like counting the electrons? Yeah. Anybody who's NH4 and counting electrons? So, I'm going to take this one. They accounted for it, except they put 8. So what I would do is I always go element, element. The last thing I do is the charge.
Wait, who rubbed out the charge?
Pardon?
Why was the charge rubbed out? I put a charge.
Yeah, you put plus 1 there. Except it's not 5 plus 4 plus 1.
Yeah.
You got a minus 1. So I always put the charge here.
Okay.
Because I'm accounting for it, and for every plus 1 charge, I minus 1 electron. So
Okay.
it's 5 plus 4 minus 1, 8 electrons.
Okay.
Does that make sense? And then from there, is that all you need? Or do you want me to go to here? Yeah. So this is the central atom method. So then I pick out the central atom, and NH4, which is the central atom. Then, put that down. You put all the other atoms around it, around the cardinal points, north, south, east, west.
Yes.
Haven't added any, taken away any electrons yet, we're still at 8.
Yeah, but
Then you bond everything once.
Oh yeah, that's true.
and
One,
also you know that
three,
the oxygen
4,
is circular.
2, 4, 6, 8
And
electrons.
6.
I've used up 8 electrons.
No, but
I have none left, I can do
6
no more
plus
bonding.
1 that is bonding with this.
However,
that is
I
7.
didn't have them.
No, it's
I'm telling you.
How many electrons are left?
If
Dude,
to
the
make a
hydrogen
bond,
exception.
it needs to have
Nitrogen
an
has
swap.
Yeah.
So it means
So
there's
then
1
you're done.
electron here.
The only thing is you know
So
it's a
there's
plus
an
1
electron
charge,
here, which
and
is
so to show
7.
charges, you just put
It has
square
6,
brackets
so
around
it
it.
needs
Because the
double.
charge isn't at any one location,
Yeah,
the whole
it should
thing.
be. Yeah, there should
Does that
be.
make sense? Anyone else want me to go over any of them, including like the double bonds?
Yeah.